Picture this. You open up your Cambridge 7702 physics exam paper. You immediately spot a high-mark question on the magnetic properties of matter. And boom, you just start writing down absolutely everything you've ever memorized about electric motors and hard drives. You walk out of there thinking you've totally nailed it. But when results day rolls around, those marks are just gone. Your grade boundary plummeted, and frankly, your confidence takes a massive hit. So why does this happen? Well, it's because answering a Cambridge physics paper isn't just some basic memory test. It's actually a high-stakes, highly strategic chess match against the examiner. Welcome to this explainer, where we're going to decode the examiner's strategy together and figure out exactly how to turn your solid-state physics knowledge into an unstoppable, high-scoring checkmate.
Right off the bat, you need to know that the entire magnetic matter section of the syllabus is paved with this invisible three-move trap, and literally thousands of students fall right into it every single year. The examiner knows exactly what you're going to do. Move 1, they'll hit you with a broad question about magnetic materials. Move 2, you'll confidently list off a bunch of properties, but, and here's the catch, you won't link them to microscopic physical causes. Then move 3, the examiner strikes, giving you absolute 0 marks for your disconnected theory. This whole trap is completely designed to separate the students who truly grasp solid-state physics from the ones who are just desperately reciting glossary terms from a textbook.
Okay, let's dive into this absolute tragedy of an answer. Magnetic materials are magnetic because they have a magnetic field and are used in motors. Oof, it kind of hurts to read, doesn't it? This right here is the ultimate, incredibly common student mistake. The student is confusing a basic label with an actual scientific explanation. It's essentially like saying water is wet because it has wetness. In a high-level exam, just stating that a material has a certain property without linking that property to its atomic arrangement, or bonding, or carrier motion, or field response, yeah, that is a guaranteed way to lose points. We really have to prove to the examiner that we understand the microscopic chain of cause and effect.
All right, Section 1, Origins of Magnetic Behavior. This is how we escape the trap using microscopic truth.
So, the absolutely crucial thing to wrap your head around is that magnetic behavior isn't just one single phenomenon. It's actually a whole family of behaviors. At the very core of this big idea is the simple fact that magnetism arises from two distinct things, moving charges and electron spin. That is our microscopic foundation right there. Now, depending on the unique atomic arrangement and the internal interactions inside a solid, different materials are going to react really differently to an external field. Some will stubbornly align slightly against a field. Others will align slightly with it. And a very select few will develop this massive, powerful domain-based magnetization. The external field could be exactly the same in all three scenarios, but the internal structure entirely dictates the physical response.
Let's see how this all builds step by step, because this three-step chain is exactly how your thinking needs to be structured on the exam. You literally can't jump straight to step 3. It all starts at step 1. Individual atomic magnetic moments which are created by those moving charges and electron spin. Then we move to step 2. How do those atoms actually interact with their neighbors? We call this collective atomic ordering. And finally, step 3. If that collective ordering is strong enough, it creates these massive blocks of aligned atoms known as domains, which leads to macroscopic measurable magnetization. If you can describe this exact domino effect from microscopic cause to macroscopic effect in the exam room, you are actively dismantling the examiner's trap.
Stick with me here because in just a few minutes, we're going to uncover the ultimate examiner clue. It's this very specific way of wording an evaluation that instantly elevates your answer from just average to top band. But if we try to use that clue without fully understanding the underlying structure of a perfect answer first, it's just going to fall flat. So we need the master framework to make this clue completely obvious. Moving right along to Section 2, the 3-part answer framework. Basically your winning strategy.
Anytime a big macro topic in solid-state physics comes up, please do not just reduce it to a one-line definition. Instead, let's run it through this 3-part framework. First, you ask, what is the structure or process? For instance, electron spin and moving charges. Second, why does it happen? What's the mechanism? Well, the collective ordering forces alignment. And third, what's the observable, measurable effect it produces? A weak or strong field response. Or think about atomic arrangement. The internal structure reacts to an external field, resulting in domain-based magnetization. This model is an absolute game changer because it takes all those disconnected, memorized facts and turns them into highly usable understanding. When your paragraphs are organized around mechanism and consequence, the examiner literally has no choice but to award you the marks. Remember, every single time you drop a new vocabulary word, it must be anchored to an observable property. This framework is your anchor.
On to Section 3, Real-World Magnetic Applications. This is exactly where you secure those final, hard-to-reach evaluation marks. Real-life scenarios are so important because they prove to the examiner that you understand why the physics actually matters beyond the blank page. We're talking about real stuff here. Transformers, inductors, electric motors, hard drives, medical imaging systems. But here is the exact spot where points constantly bleed away. Students completely forget to mention the physical constraints. Listen, if you're evaluating a material for a transformer core, you can't just say, oh, it's highly magnetic. No way. You have to talk about operating temperature limits, because thermal energy actively disrupts that collective atomic ordering. You gotta discuss material purity and structural atomic order, because defects will physically prevent those magnetic domains from aligning properly. And you must factor in the external magnetic field strength. These specific constraints are your evaluation goldmine. For sure, always state one benefit and one practical limitation based on these constraints before you wrap up your answer.
All right, Section 4, Flawed versus Perfect Answers. It is time for our Spot the Error climax. Let's see this in action.
Let's look closely at the flawed answer first. The material has strong magnetization for hard drives. Now, it's not necessarily false, but it's totally empty. There's zero mechanism there. It's going to score terribly. Now listen to the perfect answer. This brilliantly illustrates that framework we just talked about. Strong domain-based magnetization, bam, that's your observable effect, arises from collective atomic ordering. That's the microscopic mechanism and structure, ensuring data stability in hard drives under external fields. There's the real-world application directly linked to an environmental constraint. This right here is that examiner clue I promised you earlier. Exact, perfectly matched language connecting the microscopic cause straight to the macroscopic constraint. It's structured, incredibly disciplined prose. When the examiner reads a sentence like this, they instantly know you have a deep structural grasp of solid-state physics. Full marks every time.
Let's lock this whole thing in with a rapid, high-energy summary. If you want to pull off a flawless checkmate against the examiner, here is your sequence. Move 1, define the core term first. Don't just slap a label on it, define the actual physics. Move 2, develop your explanation logically, mapping that journey from microscopic mechanism to macroscopic effect. Move 3, apply this concept to a real material or device to prove you get the practical side. And the final, winning move, evaluate the scenario by dropping one benefit and one specific limitation based on temperature, purity, or field strength. If you can actively recall and summarize a topic using these trigger statements in under a minute, you are completely bulletproof.
So, we now have the exact strategic framework you need to master the theory of magnetic matter. But as you know, understanding the theory is only half the battle. What happens when the examiner throws a massive, wildly complex mathematical application your way? Imagine a failing transformer core where thermal disruption is literally destroying the atomic order. How on earth do you calculate the exact magnetic flux linkage as the whole system starts to break down? That is an incredibly difficult 9702 past paper scenario, and we absolutely need to know how to solve it. But don't worry, the full mathematical checkmate is waiting for you in our next explainer. We've got the theory down, now let's go master the math. I'll see you there.